So let's have a think about this idea of work done by a force. And so what we're saying here is we've got a force that's applied to a 10 kilogram mass, and the work done by that force is just equal to the force times the change in displacement in the direction of the force. And so in this case, so we can just write down, let's just get an answer here. So we're going to have the work done, which is usually written as a U, is force times change in distance, or change in displacement. And so the distance travelled with that force applied. So in this case, it's just going to be 50 times 10. And work is a measure of the transfer of energy. And so that's going to give you 500 joules. And it's best to work with, for these equations, it's like the Newton's second law. You should be using newtons plus kilograms and meters and seconds and joules. Okay, so stick to those. So use the units. And you can change it to kilojoules or something at the end, but it's safest to use units. So you've got mass as in mass is kilograms. So you should be using kilograms, meters, seconds, newtons. That's what you should be using. And for energy, you'll use joules. So these are all compatible with each other. So if this force pushes this object 10 meters and there's nothing else happening, it's just that force and that object, it's going to do work 500 joules. And it's talking about a transfer of energy. So this force has transferred energy to this object. And so it's doing positive work. So the work done by that force is positive if it's transferring energy to that object. And so what type of energy has that transferred to? Well, this object now has a velocity. So we can think to our equations for kinetics. So it's just going to use that equation F equals ma. So it's transferring energy to that object in the form of kinetic energy. Now you'll probably know that kinetic energy, let's say Ek, is equal to half mv squared. Comes from school. Let's have a think about if we can figure out why that is. So this force is doing some work. And so what we can think of is we can say, let's just have a think about this. Yeah, we'll stick with that, F equals ma, so Newton's second law. But we can think about our equations of motion now and have a think about those. And so this is going to give us a constant acceleration because this force is constant, therefore acceleration is constant. So the acceleration is just going to be, the acceleration at time t is going to be constant, a naught. The initial acceleration will always be the acceleration. The velocity at time t, so just thinking through all the equation, is v naught plus a naught t. The displacement at times t, it's going to be s naught plus v naught t plus half a t squared. Half a naught t squared. And then we've also got this one, v squared at a distance s is equal to v naught squared plus 2 times acceleration times distance. Now, we're talking about work as a force times a displacement, and so it's probably going to be this, and then you maybe remember that your kinetic energy is half mv squared, so it's likely we're going to use this equation here. So let's have a look at what happens with that. So for this situation above, and so let's say, so the velocity at a given displacement for an object that's being pushed by a force and nothing else is happening is equal to, so let's just say it has no initial kinetic energy, and so v naught is just equal to 0. So therefore that's going to be equal to 2 times the acceleration times the distance traveled. This is actually s minus s naught. And so this is really delta S, okay, the change in displacement. Now, if we've got a force applied to an object like this, then we're going to have v squared s. I'm just going to write that as v squared. It's just going to be 2 times. Now, the acceleration is just equal to the force you're applying. So this force here divided by the mass. So force divided by mass times delta S. What we can do here is we can start to rearrange all this. So this force times the delta S, that's just the work done. Force times delta S is equal to the work done. So I'm just taking these, and then I'm going to divide this side by 2 and multiply it by m. And so I'm going to get divided by 2, half times mv squared. And so for this situation here, the work done on this object is being transferred to kinetic energy, and that's where this comes from. So you can tie these different concepts together using our equations of motion. So work done here is just being transferred to kinetic energy, and the kinetic energy associated with a moving particle is just a half mv squared. So work done equal to that, which equals to the gain, Ek, so kinetic energy. Okay, it's just equal to the gain in kinetic energy for that particle.
So let's just make this a bit more real by putting some actual numbers in. And so let's just think about our kinetics. So just forget about the work being done for the moment. Let's just think about our kinetics, and we'll just figure out how fast would this ball be going by the time it gets to this point. And so we know the force applied, and so we can use Newton's second law, F equals ma, to figure out the acceleration. And so that's kind of what we were doing here. So the acceleration, and it's constant acceleration because it's constant force, is just force divided by the mass, which is equal to 50 divided by 10, which equals 5 meters per second squared. So that's all good. And then we've got this equation here to figure out the velocity at a given distance when you've got constant acceleration. So just coming from this one, so equation 4. And so therefore we're getting, we know that v squared is equal to 2 times the acceleration times the change in distance. So it's 2 times 5 times change of distance was 10 meters. So we're just figuring out what the velocity of this object would be after 10 meters. So v squared is going to be 2 10 100. So therefore at 10 meters, the velocity would be equal to 10 meters per second squared, and therefore the kinetic energy is going to be a half mv squared, which is a half times the mass is 10 times the velocity is also 10 squared, so it's 5 times 100, which is 500 joules. Okay, so just doing the same thing as I'm doing here, but just doing it with some numbers in it. And so what we can see is the work done by that force is just equal to the gain in kinetic energy by that object. That's all the work is saying. So whatever's applying this force, it's transferring energy to this object, and the gain in kinetic energy is just equal to the work done.